National Academy of Mobile Electronics is proud to present a series of training videos for the consumer electronics industry. Each video focuses on a specific area of training with information that has been compiled and painstakingly applied over several years. These videos will make a great addition to your video training library, and if you're just getting started, they will save you hundreds of hours of head scratching. So sit back, take notes, and enjoy. Here's Mike Breault.
Hello, I'm Mike Breault. Welcome to the National Academy of Mobile Electronics. NAME has been providing quality training videos to the mobile electronics industry for over 2 years now. And now, NAME is offering training and instructional videos for the do-it-yourselfer. Each video covers key points discussing the fundamentals of mobile electronics installation. You'll receive easy-to-follow, step-by-step instruction from the same company that trains professional installers around the world. A woofer out of its enclosure is about as dynamic as a stereo with no amplifier. A poorly designed enclosure can make a good speaker sound bad, and a well-designed enclosure can make an average speaker sound very good. Now let's look at a few of the supplies we will be using to accomplish our woodworking projects. Remember, using good quality tools and materials will make a difference in your finished products. Let's take a look at some various woods and go over a few examples of which woods are optimum for our applications. Here is an example of plywood. It has many fine uses in and around the house, but its fibrous, knotty finish make it an undesirable choice for our woodworking projects. Hardwoods also have their place, but cost is definitely a drawback when it comes to automotive applications. Here we have particle board. Many speaker enclosures are constructed with it for several good reasons. One is its density, which lends to good acoustic characteristics, and the cost is very affordable. Finally, we have medium density fiberboard, or MDF. It is highly compressed and has a paintable surface, which makes it a snap to get a high quality professional finish. Next we have our backed carpet. This carpet is very easy to cut and works well on square shapes. Here we have some 3M spray glue. We will also need a good wood glue. Silicone will give us our airtight seal, which is vital when building speaker enclosures. Shooter screws and brad nails are a must to ensure strength to all of our woodworking projects. Here we have some good quality scissors and a razor knife with blades. Here we have a few measuring devices. You will find many uses for a carpenter's square. A ruler for marking straight lines, a tape measure for various measurements, and an angle finder, which is critical when building custom enclosures when you need to find seat angles. The taper jig is very handy when cutting the uneven sides for mini truck boxes. This is the ever popular circle jig. Of course, it is shop made, but its flexibility is endless. Clamps often lend that much needed second set of hands for many of our projects. Here is our drill press and belt sander. The Makita belt sander gets rid of uneven surfaces to prepare for the finish sander. The finish sander makes quick work of body fillers, fiberglass, and wood finishes. Several different styles and sizes of wood bits and augers are used throughout our endeavors. An air stapler or brad nailer expedite the time spent on assembly and is a very valuable tool. A laminate trimmer comes in handy to give your work a professional finish. Here we have a Porter cable router. The Bosch plunge router is a great tool for industrial sized jobs, and when coupled with a flush trim bit, it's a must for the duplication of shapes and forms. Here we have a Bosch jigsaw. And finally, a table saw or some type of saw to get good accurate cuts. Remember, it is always important to demonstrate good safety habits. Safety goggles and dust masks are very important and should be used whenever using power tools. Now we will define Thiele small parameters, which make our enclosure building ventures much more comprehensive. The Thiele small parameters which we are most concerned with are going to be the FS, which is the frequency in which the loudspeaker resonates in free air, and is also where the loudspeaker operates most efficiently. Next we have the QTS. This is a measure of the speaker suspension. The stiffer the suspension, the higher the QTS will be. Finally, we have the VAS. This specifies the airspace in a sealed enclosure which would match the compliance of the speaker. Once derived, these parameters will make it possible to predict the response of your enclosures. Now, let's move on to basic geometry. Here we will discuss the basic formulas for finding the area of a particular shape. First, we will begin with a rectangle. To find the area of a rectangle, you simply multiply the length times the width. For a triangle, you multiply half the base times the height, and for a circle, the formula is pi r squared, or 3.14, multiplied by the radius twice. Now, in figuring the volume of a particular shape, the formulas are as follows. For a rectangular box, simply multiply length times width times depth, as demonstrated here. The length is 12 inches, multiply that by the width, which is 10 inches, and now multiply that by the depth, which is 5 inches, for a total volume of 600 cubic inches. Now for a triangular shape, you would divide the base by 2. In this case it would be 6 inches divided by 2 to get 3, and multiply that by the height, which is 12 inches, and multiply that by the width, which is 18 inches, to get a total volume of 648 cubic inches. Now let's look at the formula for a cylindrical shape. Here we have a 6-inch diameter cylinder that is 10 inches long. To determine the total volume of this cylinder, simply find the radius, which is half of the diameter, or in this case 3 inches. Now square that. In other words, multiply 3 by itself to get 9. Next, multiply 9 by pi, or 3.14, to get 28.26. And finally, multiply that by the depth, which is 10 inches, to get a total volume of 282.60 cubic inches. Now in many cases, your enclosures may take the shape which would involve more than one of the shapes which we just covered, and at this time we will discuss an easy way to determine the volume of such shapes. Here is a basic shape of a mini truck box. To derive a volume for this shape, simply add our top, which is 3 inches, to our bottom, which is 6 inches, to get 9 inches. Then divide that by 2, which is 4.5. Now multiply that by the height, which is 12 inches, and finally multiply that by the width, which is 18 inches, to get 972 cubic inches. One important thing to note is that these are inside dimensions. So if you have taken outside dimensions and you have used 3/4 inch stock, reduce your measurements by 1.5 inches. Now let's see how to convert the 972 cubic inches into cubic feet, since cubic feet and liters are used in the VAS of a speaker's Thiele small parameters. It takes 1,728 cubic inches to make up a cubic foot. So if we divide the total volume of our enclosure by 1,728, this will tell us how large our enclosure is in cubic feet. In our case, our enclosure is 972 cubic inches. So 972 divided by 1728 is 0.562 cubic feet, or just over half a cubic foot. To convert that to liters, you need to know that there are 28.317 liters in 1 cubic foot. So simply multiply 28.317 by 0.562 and you'll see your enclosure is 15.914 liters. The last formula that we will cover in our geometry section is finding the hypotenuse of a triangle. The hypotenuse is the long side of a triangle, which in many cases is the side of an enclosure that remains unknown after taking measurements from behind the seat of a pickup or many other wedge-shaped areas in a vehicle. In this case, we have an enclosure in which the top is 3 inches, the bottom is 6 inches, and the height is 12 inches. As you can see, the unknown side is the long side, which is the front of the enclosure. Now to find this side, we must first break the shape down, which consists of both a triangle and a rectangle, and find the dimensions of the triangular portion of the enclosure. To do this, let's draw a line down from the point where the triangle begins to a point where it is 90 degrees from the bottom of the shape. Now in separating the two shapes, you will see that the bottom of our triangle is 3 inches and our back or height of our triangle is 12 inches. Next we will designate sides of our triangle. Side A will be our base side, side B will be our back, and side C will be the front or the hypotenuse. Note that side A and B could be either of the two known sides, but side C will always be the hypotenuse. Now the formula to find the hypotenuse is side A squared plus side B squared will equal side C squared. In other words, 9, which is equal to side A, or 3 squared, added to 144, which is equal to side B, or 12 squared, is equal to 153. Now since 153 is equal to side C squared, we must then find the square root of 153, which is 12.37 inches for side C. Regardless of whether you use a rectangular or cylindrical port, displacement is determined from the outer edges of your ports. If you remember back to the section on determining volumes, that will come in handy in this section. Simply find the volume of your rectangular shape or your cylindrical shape and add that to the optimum volume needed for your enclosure. Now in determining the displacement of your speaker, the formula is as follows. Simply measure the depth of your woofer from the edge of the basket to the back of the magnet and cube that. For instance, if your depth was 3.75 inches deep and we cube that, our answer would be 52.73. Next, multiply that by 1.243 to find the displacement of your driver. For example, this displacement of this driver would be 65.6 cubic inches. This measurement is not exact, but should be within 10% tolerance, which is acceptable. Okay, here are the formulas pertaining to sealed box enclosures. The first formula will determine the optimum box volume based on preferred QTC. The QTC is also referred to as the system Q and is simply the Q factor when combining both driver and enclosure. QTC is only referred to when dealing with acoustic suspension type enclosures. A preferred QTC is around 0.707 for smooth base and good transient characteristics. Too far under that number will tend to lack bass, and over that will tend to be too boomy. The way this formula works is simply plug in the desired QTC of your enclosure, plug in the other parameters such as VAS and QTS in their area of the formula, then calculate. For example, if we prefer a .707 QTC with a driver whose parameters has a VAS of 4.2 cubic feet and a QTS of .38, start by dividing .707 by .38 and square that, then subtract 1. .707 divided by .38 is 1.86. Now square that to get 3.46 and subtract 1. Then divide VAS, or 4.2, by 2.46 to find our enclosure should be 1.7 cubic feet. Here are the formulas for designing an optimum tune-ported enclosure with zero ripple. Ripple is described as the deviation in response during the base transition. Plus or minus 2 dB is acceptable ripple. The last set of formulas we must familiarize ourselves with before moving on with actual design are those dealing with port lengths. As you can see, vent radius is equal to vent diameter divided by 2. The formula then for vent length is 14630,000 times vent radius squared, then that is divided by 1728 times box volume, or VB, times box frequency, or FB, then divide the top total by the bottom total and subtract the product of 1.463 times the vent radius. Here we have a loudspeaker with the following Thiele small parameters: a QTS of 0.52, a VAS of 3.3, and an FS of 34 Hz. We will be constructing our cabinet out of 3/4 inch MDF and would like to achieve a QTC of 0.8. Since size is not an issue with this enclosure, we have the option of utilizing a specified or preferred QTC. This being the case, the formula that we will use to design our enclosure is the box volume from QTC on page 3 of your NAME reference guide. Box volume equals VAS divided by QTC divided by QTS squared minus 1. Now we will plug our known values into the formula. 3.3 for VAS, 0.8 for QTC, and 0.52 for QTS. First divide 0.8 by 0.52 to get 1.54. Next square that to get 2.37. Then subtract 1 and your formula should look like this: 3.3 over 1.37. Now divide 3.3 by 1.37 to find your box volume in cubic feet. An important note when working with these formulas is if your VAS is given in liters, then the final results will also be in liters for your enclosure. In this case, our VAS was 3.3 cubic feet. Therefore, our final equation will be in cubic feet. Our calculations show that our enclosure should be 2.41 cubic feet. Now this is internal volume. Next, we must figure displacement of the driver and braces. Let's begin by converting our enclosure from cubic feet to cubic inches. Simply multiply 1728 by 2.41 and you'll get 4164.5 cubic inches. Next, figure the displacement of your driver. In this case, our woofer is 4 inches deep. Now, follow the displacement formula on page 6 of our reference guide. To see, you must cube 4 to get 64, then multiply that by 1.24 and you'll get 79.36 cubic inches. Now add that to your initial enclosure size to get 4243.8. Again, Remember, these are internal dimensions and we will compensate for wood thickness in the final step. Before we wrap up with our sealed enclosure, here are a few more helpful tips. If you are limited for space when designing a sealed enclosure, by adding a light batting to your enclosure, its mass will give your enclosure an apparent increase in volume of about 15%. Next, if you choose to design an enclosure with multiple drivers, simply multiply the VAS by the amount of drivers you are using, and the QTS and FS will remain the same. It is preferred that your woofers are installed in a vertical fashion for long-lasting, accurate results. At this point, let's calculate the outside dimensions of our enclosure. When designing an enclosure, it is recommended that we derive a cut sheet before we begin cutting. As you can see in our illustration, we must add 1.5 inches to both dimensions of side A and B. Sides A and B are 20.41 by 16.20, and after adding 1.5 inches, you'll find side A and B are 21.91 by 17.7. On side C and D, we'll add 1.5 inches to the length dimensions and leave the width dimension alone. So side C and D would be 21.91 by 12.85. And our last two sides, E and F, since it is inserted into the other four sides, will remain the same, or 16.2 by 12.85. As you will notice, the sides will always support the top and bottom, and the portion of the enclosure which houses the driver will fully cap the end of the enclosure. Now, when cutting the sides for your enclosure, make your cut sheet such that you will make all similar cuts without moving your fence. For example, here are the dimensions in which your enclosure sides must be cut to. Make a cut that is 21.91 inches wide and long enough to make 4 cuts, the first two being 17.7 inches, then move your fence to 12.85 inches for the next 2 cuts. Now we have sides A, B, C, and D, and with your fence remaining in the 12.85 inch position, cut a final piece long enough to get 2 cuts at 16.2 inches for sides E and F. By making all similar cuts simultaneously, your cabinet should go together perfectly. Now let's design a tune-ported enclosure using this loudspeaker with the Thiele small parameters of 3.4 for VAS, a QTS of 0.27, and an FS of 29 Hz. First, let's plug our Thiele small parameters into the optimum tune-ported formula found on page 4 of our reference guide. This will tell us the size of a perfect enclosure. Let's put 0.27 here for QTS and 3.4 here in place of VAS. Calculate 0.27 to the exponent of 2.78 to get 0.0262. Then perform your multiplication. 15 times 0.0262 is 0.393 times 3.4, and you'll see that the optimum enclosure with the Thiele smalls given would be 1.34 cubic feet. Now, to determine the frequency in which we should tune our enclosure, let's use the formula to find FB, or box tuning frequency, also found on page 4. This is the formula. Now simply plug your parameters into the formula as they apply. 29 Hz for FS times 3.4 for VAS divided by 1.34 for box volume with an exponent of 0.31. Remember, grouping symbols first. 3.4 divided by 1.34 for 2.54, then exponents, 2.54 to the 0.31 exponent, for 1.335 times 29 Hertz to get a box tuning frequency of 38.71 Hertz. And you're ready to move on to vent length. Within grouping symbols first, FB squared, or 39 Hertz squared, is 1521, multiplied by VB, or 1.34, is 2038, times 1728 is 3521664. Next, 1.463 times VR, or 2.5, is 3.66. Now on top, VR, or 2.5 squared, is 6.25 times 14630000 is 914,37500. Now divide that by 3521664 to get 25.96. Then subtract 3.66 to get a port length of 22.30 inches long. Here's where we can get creative. It is important to note that the larger the area of your port, the longer it must be. So we suggest a smaller area port if there is a need to make it shorter. However, a smaller area in a round port has been known to cause chuffing or excessive port noise. So it is recommended to use slotted ports, which allows you to use a smaller area without compromise. To use the formulas in our study guide, simply convert a round port to a rectangular port using the formula we showed you in the geometry section for area of a circle, pi r square. For instance, a 3-inch port's area is 3.14 times 1.5 squared for an area of 7.06 inches. Now we may convert this to a rectangular 1 inch wide by 7.06 inches long. This would allow us to use a 3-inch port where a 5-inch round port would be recommended. Now to calculate the rest of our enclosure, take your optimum enclosure volume, which is 1.34 cubic feet, convert it to cubic inches, add speaker displacement and vent displacement, and repeat the same process we used earlier in this video. Now let's build a box to a custom design. Here is an illustration. Take 1.34 cubic feet times 1728, that equals 2315.52, plus our speaker displacement of 80 inches, and our port displacement of 54.12 after recalculating the length for a 3-inch equivalent port, and we have a gross total of 2449.64, which we'll round up to 2450 cubic inches. Now let's take a few dimensions from behind our seat to find we have 3 inches on top, about 7 inches on the bottom, and a height of about 18 inches. To find out what our width will be to equal the volume required, remember, add the top to the bottom and divide by 2 to get 5. Now take your gross number of 2450 cubic inches, divide by the two known values, and you'll reveal the last dimension. 2450 divided by 5 is 490, then divide by 18 and you'll find 2722 inches wide. Now remember, these are all inside dimensions, so be sure to account for wood thickness when designing your cut sheet. Section, we will be constructing a planar isovent. This unique design allows us to have our drivers coupled on the same plane, helping to reduce the depth of our enclosure. This type of enclosure is ideal for maximizing subwoofer response in mini pickup trucks and other small restrictive areas. Here we will be constructing a mini truck box utilizing this design using the Kicker 8-inch loudspeakers shown here. we know that the overall enclosure size was 1.486, and for this type of enclosure we will be slightly increasing the size by adding an acoustic coupling cavity. This cavity will take up a total of 0.13 cubic feet, and adding that to our initial volume of 1.486, we find a total volume of 1.61 cubic feet. Now let's design the enclosure using this volume. First, let's take a few measurements from behind the seat of our pickup. Our top measurement is 4.5 inches, our bottom measurement is 7 3/4 inches, and our height is about 15 inches. Now, with these three dimensions, let's calculate what the width must be to stay with our original volume previously determined. First, subtract 1 inch from each dimension, since we will use 1/2 inch MDF to build our enclosure. Next, add the top, which is 3.5, to the bottom, which is 6 3/4, to get 10 1/4, then divide by 2 to get 5 1/8. Now, take our total internal volume of 1.61 and multiply that by 1,728 to get 2,782 cubic inches. Now, divide 2,782 by the average that we found for the top and bottom, which was 5 1/8, and you should get 542.8. Now, divide 542.8 by the internal height, which is 14 inches, and this determines the inside width of our enclosure to be 38.75. Now here's a look at our box dimensions. Our top is 4.5, our bottom is 7 3/4, our back is 15 inches, and our width is 40 1/4 inches. Remember, we've added 1 inch for wood thickness on all dimensions and 1.5 for our width to account for the center divider between the two enclosures. Use the formula previously taught to determine your front dimension. In this case, we find it to be 19.44 inches after accounting for wood thickness. Now here is a breakdown of our cut sheet. We will now cut our sides, top, bottom, back, and front. As you can see, we also have an insert piece to divide our two cavities. Next, we will need to build our coupling cavity. For this enclosure, we will first design the baffle out of 1/2 inch MDF, just large enough to house our drivers, leaving about 1.5 inches between the drivers and the edges all the way around. Now, use the baffle and with the flush trim router bit, duplicate 2 more pieces of 1/2 inch MDF. These 2 will eventually become the rim of our coupling cavity. Now we will cut out one of the pieces designated to be the rim using a boss jigsaw, leaving about 1 inch thickness from the sides. Now duplicate this piece using the router after you have glued the 2 together. You now have the rim. Next, take a sheet of 1/2 inch acrylic and symmetrically drill your holes in it to attach it to your baffle piece for duplicating this pattern. Once finished, take the flush trim bit and router your acrylic to match the shape of your baffle. Now we move on to the tricky part. Take an 1/8 inch dado bit for your router with a 1/4 inch shank and raise it above your table about 1 1/4 inches. Now attach your plexiglass to the rim pieces, which are 1 inch in thickness. After peeling the paper off the top side of your acrylic, proceed to carefully router a groove in your plexiglass, allowing the 1/4 inch thickness of the router bit to ride along the inside of the rim. We will now glue and attach our baffle piece and rims to the inside front piece of our enclosure. Note, center the baffle between what will be the 2 cavities in your enclosure. Once attached, drill a hole in the face piece and router out the front flush with the rim of the coupling cavity. Now, use a rabbet bit and countersink down a 1/4 inch around the baffle so the acrylic face may be recessed somewhat. In this type of enclosure, all seals are very critical, so don't spare the silicone in the areas such as the baffle seal and so on. On this enclosure, we have constructed our port in the shape of a U out of 1/2 inch MDF, and we will router the inside edge using a roundover bit to eliminate potential port noises. Now, let's construct our top, bottom, and sides. As you will notice, we have cut a notch into our centerpiece to compensate for our baffle insert. Next, let's attach the port. To do this, glue the port to the side of the enclosure which will be ported, in this case the left side, then clamp it down and nail it in place. Once in place, router the opening for the port out of the top of the enclosure. Next, we will attach the framework to the front of the enclosure. Once the framework is secured, seal all inside edges using silicone. Once we finish sealing the top, bottom, and sides to the front and baffle, we can attach the back. Simply spread a bead of silicone around the edges, then attach the back. The silicone must be applied in this stage since there is no way to get all of the corners once the back is attached. Now, take your roundover bit and round over the opening for the port, leaving a slight lip to flush out the opening with the carpet during the upholstery stages. Now, on the front side, we will add the carpet to the baffle area before inserting the speakers. Again, remember that all seals are critical, so be sure your speakers are well seated and tightened securely. Now, to get an airtight seal around the acrylic face, we have spread silicone around the countersunk edge evenly and allowed it to dry. The purpose for this is to make the removal of the acrylic piece possible if the drivers must be accessed in the future. After peeling the paper away from the back of the acrylic, we have secured some masking tape to the front inside the groove, which we routed earlier. Now, attach the acrylic face piece and tighten it securely, ensuring an airtight seat. We are now ready to upholster our enclosure. The critical portion of upholstering this box is in the edge around the acrylic. Once the enclosure has been covered with carpet, pull up the edges around the acrylic and cut it out with a pair of scissors, leaving about a 1/4 inch or so to tuck into the groove. This step gives a beautiful finish and hides all of the holes and screw heads. And to change out the speakers, just pull it out of the groove and remove the screws and the panel. Now, when putting on your terminal cups, be sure to wire them out of phase inside the enclosure to ensure proper electrical phasing when the box is installed. Here is a look at our finished product. On behalf of the staff here at NAME, I would like to thank you again for your support. I'm Mike Breault. Goodbye for now.
This concludes our video presentation. For suggestions for new videos or the release of other training videos, call NAME